In the first part, we have learned how to compute the multiplication and division of power series, which is section 73. Now, let's see the exercise. How to apply the theorem or just method here. The first problem is to use multiplication of series to show that this equals to this expansion. So e to the g divided by g times g squared plus 1 is equal to 1 over g plus 1 negative 1 over 2 g negative 5 over 6 g squared plus. Here the circle of convergence functional disk given by this modulus of g is greater than 0 and less than 1 here. Here we first check what the singularity for the given function is. In this case, g is not equal to 0 and plus minus I. Excluding these 3 points, this function is entire because e to the g is entire, and also denominator is the product of two polynomials. First is g and second is g squared plus 1. So we are going to use the two Maclaurin series expansion among six Maclaurin series we know. Here first 1 over 1 negative g can be expanded by using this form 1 plus g squared plus keep going this like this, and e to the g can be expanded by using this formula with the convergence condition, this and this. So first we want to modify the given function by this 1 over g times g to the e to the g times 1 over g negative g squared here, because we gonna use this first Maclaurin series expansions. Then we get this for this summation n is equals to 0 to infinity negative g squared to the n. And for this function e to the g can be replaced by this expansion summation n is 0 to infinity g to the n divided by n factorial. And for this case we have nothing to do, just multiply these terms, expand series this time and series and this series. So finally we get this 1 over g plus 1 negative half times g negative 5 over 6 times g squared plus over the functional disk. So we have the result for this problem. Because singularities happens with this point, but with this condition, I mean that the functional disk given by this modulus g is greater than 0 and less than 1. Do not include these 3 points. So the condition holds for this expansion. Okay, next move to the second problem. By multiplying two macroequation series term by term, show that the problem A, e to the g times sine g, can be expanded to g plus g squared plus 1 over 3 times the g cubed plus, where modulus of g is less than infinity. Here, the function e to the g and sine g are both entire. So the product, which means that e to the g times sine g, also entire. So we can use the Macron series for these two functions, e to the g and sine g. I mean that these two formula just replaced by the functions with these expansions here, then multiply term by term, and then get the terms of same powers in terms of variable g here. Then first multiply 1 and g, then we get this g plus. Then for the second part, here multiply these two terms, then g squared. There's no other terms for the second part, so move to cubed. For this, we consider these two terms, then multiplied, we get this 1 over 2 factorial, and also we get this result for the cubed powers, negative 1 over 3 factorial here. So the coefficient of cubed powers here, half negative 1 over 6, then we get this 3 over 6, negative 1 over 6, then we get this 2 over 6, which we can cancel. Then we get this 1 over 3 here, we get this. And like this, we can compute every coefficient for other powers. Then we get this, which validity of condition, we get this, because these functions are entire. So now move to the second problem, 2 to the b, I mean that e to the g divided by 1 plus g. Quite similar way, we can expand this function by using the Macron series. First is 1 over 1 negative g and e to the g. We know where, because the function e to the g is entire. So, but in this case, we need to exclude the singularity of the function 1 over 1 plus g. Negative 1 makes the denominator 0 here, so the valid condition should be modulus of g is less than 1. So we just apply the Taylor series here for this by using the first Macron series here. 1 over 1 negative g is equal to summation n is equal to 0 to the infinity g to the n. In this case, we need to modify slightly here, like this. 1 over 1 negative negative g, which is actually the given function, 1 over 1 plus g. But we can apply the first Maclaurin series with this form. Yeah, here, exactly same, but with the different result, where the validity condition is the same as the Maclaurin series of the function 1 over 1 negative g, because modulus negative g is equal to modulus g here. So therefore we get this for this function, product of two series, then we multiply term by term and arrange the terms with the same power, then we get this. This is quite similar problem to A. So we need to move to problem 3 by writing uh, 1 over sine g cosecant g, and then using division show that cosecant g is equal to 1 over g plus 1 over 3 factorial times g, and 1 over 3 factorial squared negative 1 over 5 factorial g cubed plus keep going like this, where the validity condition given by this modulus of g is greater than 0 and less than pi. In this case, for the singularity, we need to exclude the point g equal to n times pi here, and it's a natural number which is equivalent to this condition sine g is equal to 0. We know that sine g can be expanded by this formula, which is exactly Maclaurin series with this validity condition. But we do not want to include the singularity, so we need to exclude from this condition. Then we get this validity condition, modulus g is greater than 0 and less than pi. And then we just do division. I mean that 1 over sine g here. Just write 1 here, and then this series left hand side. Then just arithmetic by using this form. So first we write here 1. Here 1 over g, then multiply this term and this series, then write this line, then first term g times 1 over g result in 1 here, then second terms 1 over g times negative g cubed divided by 3 factorial, then we get this. Like this, we get other terms. And then subtract these two lines, and we get this. And those similar things for these series. Then we get this eventually, the result given in the problem.